All right, this is page 3 of notes 2 of Calc C, and what we're doing is we are trying to write um, Taylor polynomials, which are polynomials that follow a specific pattern. We're trying to write Taylor polynomials for a couple of functions. So let's see if we can do it. So if you remember in the last video, what we had was we already had a table constructed, and it told us the value of the derivative at a certain x value, right? So the 0th derivative is the original function. Then we went up through like maybe the 5th derivative, I don't know. And we tried to follow a pattern, and then we checked, and we actually found a polynomial that did work out. And so what we're going to do here is the same sort of thing, except now instead of just having a table that tells us, let's just look at it. Here we just had a table that like randomly kind of told us the derivatives at x equals 2. And then we wrote our polynomial. This time we have a function, and what we'll do is just create our own table. So this is a big deal, and you find yourself doing it a lot. We make the table, right? Because what we know how to do is based on having a table of values. We don't have a table, just make it. So let's see if we can do that. So the 0th derivative is the original function. So this is going to start with sine of x. And then the derivative of that is cosine. And the derivative of that is negative sine. And then negative cosine. And then positive sine. And then back to cosine. Okay, so once we have these, we need to evaluate all of them at the center. So for this particular problem, we're given the center is at 0. So we evaluate all of our derivatives at 0. So the sine of 0 is 0, 1, 0, negative 1, 0, 1. Now we have a table. So we think that the pattern that we're going to use has so the nth term of our polynomial is going to look like the nth derivative at the center times x minus the center to the nth power over n factorial. So that's the nth term, and then what we do is we just add them together. So I think what we're going to end up with here is our polynomial. Do we have a name? P of x. So P of x is going to be, so I'm going to write it out. There's a lot of these that are just going to simplify down to 0, but I'm going to write them out anyway. So it's going to be the 0th derivative at 0 is 0. Then x minus 0 to the 0. You know, let's not write the minus 0 part because it's just going to take so much space. I'll put it in parentheses though, just because this. Then I'm going to add to that the first derivative at 0, x minus 0 to the first over 1 factorial, plus the second derivative at 0. So 0, x, we're not writing minus 0, but we really should, over 2, to the second rather, and then 2 factorial. Then the third derivative, so plus negative 1, x should be minus 0, not writing it, over 3 factorial, plus 0, x to the 4th over 4 factorial, and then plus 1, x to the 5th over 5 factorial. Okay, so my polynomial cleans up a lot. So you don't want to simplify factorials, but you don't usually write 0 factorial. Like that's a weird thing to do. So this first term actually is just 0. That's 0, that's gone. So the second term, I'm just going to write x. Because 1 factorial is 1. It doesn't really hurt to simplify that one. The next thing is just going to 0 out. And then we're going to get minus x cubed over 3 factorial. And then the next thing is going to 0 out. And then we're going to get plus x to the 5th over 5 factorial. So this is our 5th degree polynomial. But look at that pattern, right? So just seeing that, you can probably guess the next term. So I think I'm going to do it in a different color. I'll do it in orange. So if I, if I had to guess the next term, I would say the next term is probably minus x to the 7th over 7 factorial. If I needed another, I would say it's probably x to the 9th over 9 factorial. So it's alternating. You're going a positive, then a negative, then a positive, then a negative, then a positive. It's alternating, plus minus. You're only getting odd powers. So sine is an odd function. And then we only have maybe a different color for this. Let's see. Sine of x is odd. P of x has only odd powers, which kind of makes sense because if you really want to model an odd function with a polynomial, it seems like an odd polynomial would also like help. So this is what we're trying to do. And now let's see how it compares. So I'm going to go to the calculator. I'm going to put in my polynomial, and then I'm going to put in the sine function, and we're just going to compare and see what happens. So P of x is going to be colon equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So like not a lot going on there. And then f of x was actually sine of x. So we want to fill in a table for f of x and a table for p of x. So I'm going to do f of x such that x equals. So you can actually just like type them all in. I'm going to do a weird thing. I'm going to do the sequence -3 plus t. T goes from 0 to 6, and it'll like spit out all of them at the same time. Oh, that's annoying. But yeah, they're exact values, so that kind of makes sense. Let's get decimals. In which case, this is like way too many to look at. But I'm going to write these in. So I'm writing these in the notes. So you should also do that if you're like trying to keep up. So -0.141. -0.909. -0.841. And 0. And then let me scroll. So I feel like 0 is always like a good spot to start scrolling. 0.841. So sine is an odd function. So like once I wrote some of them, I kind of like knew the other ones because of the sine of negative x is the negative of the sine of x. So I could actually just like take the values that I previously got and change their SIGN, but I'm not doing that as you know, as I'm talking my way through this. I didn't do that, but I could have. All right, now p of x, right? So I want p of x such that x equals, we're gonna go sequence, and same one, -3 plus t, comma 0, comma 6. I'm gonna do Control Enter because I don't want to see all the fractions that I would end up getting there. So -0.525. I'll go back to the notes in a second. 933, -0.842. That one's super close. At the center, they should be exactly the same, and they are. And then 0.842, 0.933, pretty close. 0.525. So another thing we could do is we could look at the error, right? So I could do the absolute value of f of x minus p of x such that x equals the sequence -3 plus t, comma 0 to 6. Excuse me, what the heck? And you can see the error. So this is how wrong we are. This is the difference between our approximation and the actual value. Weird thing is we don't know which one's bigger based on this because we're putting the absolute value. So you can see here this first value corresponds to x equals -3. So we're off by kind of a lot. -2, like not bad. -1, barely anything. 0, barely anything. And then it's like symmetric errors. So pretty good on like a certain interval. Let's take a look at the graph. I know it doesn't say to, but like this is something you should do. Really, really good on a certain interval. Looks like I don't like -pi/2 to pi/2 maybe. Doing a really good job. If we add terms to p of x, so p of x goes up to x to the 5th. So the next term would be minus x to the 7th over 7 factorial. Notice it's like a little better for longer. Let's add another one. X to the 9th over 9 factorial. As we add terms, as we go to infinity, if we could have an infinite number of terms, this thing is going to be exactly the same as sine. So we say it converges to sine for all values of x. If we go to infinity, if we have enough terms, eventually this will be exactly the same. That's like a big, interesting idea. So let's go back to the notes and we'll see what else we're supposed to do. And then maybe, yeah, so I'm gonna cut it here because it's gonna take just as long. So we made our own table, and then we just followed the pattern that we thought made sense, and it gives us a polynomial that matches sine very well. And we only use 3 terms. If we use more terms, it gets even better. So it's like definitely a thing that we want to pursue more of. Because like if somebody asks you what the sine of 1 is, like what are you gonna say? I'm like, I don't know what the sine of 1 is, but I do know that if I take 1 and I plug it in here, it's gonna be really close to the sine of 1. So I could say the sine of 1 is approximately 1 minus 1 over 3 factorial plus 1 over 5 factorial. If I want to be closer, I would say minus 1 over 7 factorial plus 1 over 9 factorial. If I want to be still closer, say minus 1 over 11 factorial plus 1 over 13. And you can just keep going forever. And if you go out to infinity, it's exactly the same as the sine of 1, which is a weird idea. So you got to come to terms with that. But anyway, I will be back in the next video to do more of this. So I will see you there.